So discrete time Fourier series, that is Fourier series representation of a discrete time periodic signal xn. And let me write the continuous time Fourier series here that we already discussed. If we have a signal xt and if it is periodic with period t naught, we can have a Fourier series representation. Let's say ak are the Fourier series coefficients. That means xt is that is the Fourier series representation for a continuous time signal, and we can get ak from xt using this analysis equation, xt e to the power minus jk omega naught t dt. Okay, this is the synthesis equation and this is the analysis equation. Now there is a similar expression for this Fourier series representation for periodic signal, discrete time periodic signal. If we consider discrete time periodic signal xn, let's say n is the period of that, capital N is the period of fundamental period of that signal, then we can write it as a linear combination of complex exponentials e to the power, and what is this omega naught here? Omega naught is, what is the relation between omega naught and t naught? It is 2 pi by t naught, isn't it? Omega naught is 2 pi by t naught. So here we can write, instead of t naught, here it is n. This is the only difference. Okay. Only difference is that here the period is t naught and this one. And that is not the only difference. That's why I have not written these limits of this summation. Let's say k, when k is equal to 0, what is the value of that? What is this exponential? Is it 1? I'm talking about this complex exponential. Is it 1 when k is equal to 0?
Yes, sir.
For k, when k is 1, it is e to the power j 2 pi n into n, k is 1. And if we do that, then what is the value when k is n minus 1? Is it e to the power j 2 pi? Okay, e to the power j 2 pi by n into n minus 1 n. Is it that? Now, what is the value when k is n? Is it e to the power j 2 pi n into n small n when k is n? And for k is k n plus 1? Is it e to the power j 2 pi n? Now tell me, is there any difference between this continuous time complex exponential and discrete time complex exponentials? If you consider a continuous time complex exponential e to the power j k omega naught t, if you take different values of k, you'll get different complex exponentials, isn't it? But is it the case in the for a discrete time signal, discrete time complex exponential? What about this? Can we simplify this? The small n is an integer.
So
What is
one.
this? This is 1. And what about this? Is it e to the power j 2 pi? Sorry, 2 pi n?
Yes, sir.
Yes. So k is equal to k equals 0 and k n, they are the same. These are the same. So is there any periodicity there? These complex exponentials? Can we say that
It repeats.
e to the
Yes,
power j, let's say 2 pi n, some k plus m, what will be this? Sorry, it is, sorry, not k plus n. This is n plus m. Is it same as e to the power j 2 pi? Is it same?
yes, sir.
They're the same. So there is a periodicity there. But that is not the case for the continuous time complex exponential. If you take a different value of k, you will get a different signal. Like this is a cosine signal, and if you take the kth harmonic, it is how you will get a cosine signal having the frequency k times that fundamental frequency of that signal. So they are distinct. But in the case of a continuous time, discrete time signal, they are not distinct. So can we say that if you consider this complex exponential e to the power j k omega, j. Okay, so let me write it here, e to the power j 2 pi n. And if you compute these complex exponentials for different values of k, how many distinct harmonics will be there? These are called harmonics, different values of k, that is called harmonics. How many distinct harmonics are there?
And
There are n harmonics, isn't it? If you consider a complex exponential, discrete time complex exponential signal, there are means harmonics of that. There are n distinct harmonics. Okay. And can we say another thing, like if you consider you compute this for different values of k, okay, different values of k, and if you consider any n successive values, will they be distinct?
yes, sir.
They are always distinct, isn't it? So if we understand these two properties, then you can easily understand the Fourier series representation. If you consider k n successive values of this k, they are distinct. These harmonics will be distinct, and there is a periodicity. If you these discrete time complex exponentials are periodic with period n. Okay, so let me write that expression here. If we have a continuous time, a discrete time signal xn, let's say n is the fundamental period of that signal, the Fourier series representation is ak e to the power j 2 pi n, and the summation is not from minus infinity to infinity. In the case of continuous time signal, it is from minus infinity to infinity. Here, since there are only n distinct harmonics, the summation is over this one. So this is this one. This is the discrete time Fourier series representation. We are expressing a periodic signal as a linear combination of complex exponentials, and this complex exponentials also, it is not it is from if you consider any n distinct values of k, those unique those harmonics will be harmonics of these complex exponentials, they will be unique. So we need to consider only n terms. Okay. Does this imply any periodicity in this? This is having only n distinct, like if you consider different values of k, there are only n distinct values, and we can easily take it as from 0 to n minus 1. If we take k from 0 to n minus 1, those complex exponentials will be distinct, and we can simply define like this: k is from 0 to n minus 1 ak e to the power j 2 pi by n kn. Okay, this is also possible, but here the standard definition is over any successive values of n, successive n values of k. Okay, so this is the Fourier. Okay, now the question is, these are periodic. Periodic means if you take n successive values of k, they are distinct, and then that pattern repeats. Does this imply any periodicity in a case? We have a periodic signal xn. Let's say n is the period of that signal, fundamental period. So we are writing a0, a1, a2, let's say up to an minus 1. And this is multiplied with e to the power j 2 pi. This is k is 0, 0. So this will be 1. And this one is multiplied with e to the power j 2 pi, like that. So this is multiplied with e to the power j 2 pi isn't it? You multiply this, find the summation, you will get the signal. That is a Fourier series representation. Now my question is, this is defined for any n successive values of k. That means I can take the summation from a1 up to an. This 1 to n. K summation from 1 to n. This is e to the power j 2 pi n, isn't it? Now, if this summation and this summation are the same, and we know that this value and this value are same. So what is the relation between these two? Should they be same?
Yes, sir.
For a discrete time signal, periodic signal xn, Fourier series with respect to a period n, let's say we are denoting the Fourier series coefficients by ak. This is periodic with period n. What about the Fourier series coefficients? Are they also?
Periodic with period.
They are also periodic with period n. That is a difference between continuous time Fourier series coefficients and discrete time Fourier series. In continuous time signal, for continuous time signal, there is no such periodicity. Okay, but for discrete time signal, if the signal is periodic with period n, its Fourier series coefficients are also periodic with that period. Now let's see how to find the Fourier series. If you are given a for periodic signal, how to find its Fourier series coefficients for a continuous time signal?
Yes, sir.
For if we consider discrete time Fourier series, if with respect to a period n, there ak and ak, the expression is same. Only difference is that instead of this, this is this is. So only difference is that here it is integration with respect to t. Here it is summation over n. That is the difference, because this is a discrete time signal. So it is similar expression. Going to discuss the properties of Fourier series representation. The properties are also similar to that those of continuous time Fourier series representation. We have discussed those properties in detail. So there is no point in discussing the properties again. It is similar, and you can refer to I think this is the section in Oppenheim 3.6.2. There these properties are discussed, and the many worked out examples are also given. So please go through those problems. Okay. Okay. When I say that the properties are similar, not all the properties are similar. For example, the multiplication property. What is the multiplication property in the case of continuous time Fourier series? Is this yt is bk, then xt into yt, isn't it? That is the multiplication property. Multiplication in the time domain. In the Fourier domain, it is convolution. So there is a similar property for discrete time Fourier series representation. Let's say xn Fourier series with respect to a period n is ak, and yn Fourier series with respect to a period n is bk, then xn into yn. Is it convolution of ak and bk or something different? But what is the problem if we take the convolution of two periodic signals? So we have discussed about something called periodic convolution in the previous class. So when you convolve two periodic signals, it is called periodic convolution. What is the difference between normal convolution and periodic convolution? Because if you convolve these two signals, the normal convolution is, let's say, minus infinity to infinity. This is a normal convolution, but since these two are n periodic, here the summation is over one period. Okay, that is the only difference. Other things are the same, flipping, sliding, everything is same. But when you add those, multiply those two signals and adding, you take only n successive values because it is n periodic. We'll consider an example now. Okay, before discussing an example of that convolution, can you tell me what are the Fourier series coefficients of this signal? Cos 2 pi by 3n. How many non-zero Fourier series coefficients? This is the discrete time Fourier series representation. My question is, what are the Fourier series coefficients of this cos 2 pi by 3n? So is it that difficult comparing these two?
Infinite.
So what you have to do is cos 2 pi by 3n is what? It is e to the power j 2 pi by 3n plus e to the power minus j 2 pi by 3n by 2. Now tell me what are the Fourier series coefficients? How many non-zero Fourier series coefficients? Sorry? Which are those coefficients?
By 2 and
One by two.
1 by 2 and 1 by 2.
1 by 2, 1 by 2. Is this? Okay, now let us consider an example of this periodic convolution. Okay, let us consider two signals, 1 plus cos 2 pi by 6, and this is the first signal, and the second signal, let's say xn is this, yn is sine 2 pi by 6n. If we use the multiplication property, xn into, first let us try to find the Fourier series coefficients that directly, xn into yn, that is sine 2 pi by 6 and plus, isn't it? So tell me what are the Fourier series coefficients? How many non-zero Fourier series coefficients? So this is a periodic signal with fundamental period 6. So how many non-zero Fourier series coefficients will be there? There will be 4 non-zero Fourier series coefficients. And which are those coefficients? Anyway, since the Fourier series coefficients of a discrete time periodic signal are n periodic, we need to find it for any continuous n values. Okay, so here I am trying to find the values from 0 to 0 to 5. That is, let's say this is c of k. So what I'm trying to find is c0, c1, c2, c3, c4, c5. Can you tell me what are those values? What is c0? C0 is the average value of the signal. How to get the Fourier series coefficient? You can expand this. This is e to the power j 2 pi by 6 and plus, minus e to the power minus j 2 pi by 6 and by 2j plus e to the power j 2 pi by 6 into 2 n minus e to the power minus j 2 pi by 6 into 2, isn't it? Now tell me what are these values? What is C0?
0.
C0 is 0. Then
And
this corresponds to C1, isn't it? C1. So C1 is C1 is 1 by 2j. Then C2 is what?
1 by 2j.
Sorry, there is something
Minus 1.
wrong.
Sir, you have to
Yeah,
divide by 2 also.
yeah, 1 by 2. So is it 1 by 4j? 1 by 4j, because 1 by 2 into 1 by 2j. It is 1 by 4j. This term corresponds to the second harmonic. And what about the third harmonic?
0.
Third harmonic is 0. And fourth harmonic?
0.
Is it 0? You
Minus
have to, it is minus what? Okay, we can see this corresponds to which harmonic? This corresponds to first harmonic, because this is having a fundamental period of 6. The expression is ak e to the power j 2 pi by 6 kn. Okay, so the first one corresponds to first harmonic. And what about this? This corresponds to which one? It corresponds to minus 1, isn't it? Minus 1 plus 6. So this corresponds to, does this corresponds to fifth harmonic? Is it
Yes,
that?
fifth harmonic.
Fifth. And what about this? This corresponds to second harmonic. And what about this? This
Fourth
corresponds to,
harmonic.
this
Fourth.
corresponds to fourth harmonic. So it is minus 1 by 4j, 1 by 2j. Is it that? 0, 1 by 2j, 4j, 0, minus 1 by 4j, 1 by 2j. Okay. And since this is periodic, what is this value? This one? Is it 1 by 2j? This one?
Yes, sir. And 1 by
And
4j.
minus 1 by 4j. And here this is 0 like that. Is it? It is periodic with period 6. We found it for the first 6 values here. So it is shifted version here, n periodic. And that shifting is very, sorry?
it should be minus 1 by 2j.
Yes.
Yeah, this should be
5
minus.
should be.
Yeah, this is minus 1 by 2j and this is minus 1 by 2j. Minus 1 by 2j. Okay, so that shifting is important. You need to consider that shifting when you do the periodic convolution. Now let us do the periodic convolution of this. When you multiply these two signals, can you tell me what are the Fourier series coefficients of the first signal? I am taking xn 1 plus cos 2 pi by 6n. Now we are applying the multiplication property. What are the Fourier series coefficients of this signal? Let's say xn is 1 plus cos 2 pi by 6n, and its Fourier series with respect to period 6 is ak. What are ak? Let us find it for one period from 0 to 5, a0 to a5. What is a0?
1.
A0 is 1. A0 is the average value of the signal. It is 1 because of the constant term. Then what about A1? A1 is it 1 by 2? This one? A1 is 1 by 2. Then there is only one more non-zero term. That corresponds to minus 1. So minus 1 plus 6. That will be 5. So 0, 1, 2, 3, 4, minus 1 by 2. Oh, sorry, not plus 1 by 2. Is it? One period of this Fourier series coefficients of this?
Yes, sir.
Okay, now let us take the second signal, that is sine 2 pi by 6n. Tell me what are the Fourier series coefficients? Zeroth value is 0. Here also there are there are only two non-zero Fourier series coefficients in one period. Which are those? What is the next value? Is it 1 by 2j? Next one. And then again
0,
0.
three
0,
zeros.
0, and minus 1 by 2.
Minus
Minus
1
1
by
by 2j.
Minus 1 by 2j. Now, this multiplication property states that the Fourier series coefficients of the product of these two signals, that is the periodic convolution of these two. Now, can you find the periodic convolution of these two Fourier series coefficients, this bk and ak? Can you find that? Periodic convolution means you have to keep the first sequence same, flip the second sequence, slide it, multiply those two sequences and add it. But the addition is only over one period. Is it? So let us do it graphically. I am sketching the first signal. That one is 1, and next is 1 by 2. This is 0, 1. There are three zeros, and then minus 1 by 2, isn't it? Okay, is it this is minus 1 by 2, 1 by 2. Okay, this is one period. 1, 2, 3, 4, 5, 6
Sir,
values.
it is 1 by 2, not
Oh,
minus
sorry,
1.
it is 1 by 2. It is 1 by 2. Okay, this is one period, isn't it? One period of. Now, what about the second one? You have to flip the second signal. Okay, remember this is 0. If you flip it, will you get something like this? This one is 0, and the next value is what? Is it minus 1 by 2j?
Yes, sir.
It is minus 1 by 2j. And next one is, then there are three zeros, and next one is 1 by 2j, isn't it? Is it this? You have to flip the second signal. And what about this value here? This one? Okay, this is okay, this is 0, 1, 2, 3, 4, 5. Okay. Now what about this this value? Is it 1 by 2j?
Yes.
That is minus 1. I am drawing minus 1, minus 2 because you have to slide this signal. For this case, we don't need that values outside this interval because we are doing that summation from, let's say I am doing the summation from 0 to 5, multiplying these two signals and summing over one period. Suppose I am taking summation over one period, I am taking from 0 to 5. Okay. So here we need the values only in that interval, but here we need the values outside that interval also. So what is the value of C0? C0, multiply these two, add from 0 to 5. Will you get 0? Because there is a 1 by 4j term and there is a minus 1 by 4j term. So when you add those two, you will get 0. And you can verify that. Next what you have to do, how to find C1? You have to shift this right by 1, multiply those two sequences and add from this 0 to 5, addition over one period. So how many shifts you have to consider? CK is periodic with what? CK is periodic with period 6, isn't it? So how many shifts you have to consider? Only 5 shifts. Is it? 5 shifts you have to consider. Then you can verify that you will get the previous result. Okay? You can do it later. So the point is that when you do the periodic convolution, you have to remember that you have to sum it only over one period. Okay?